Okay, this is the lecture video for MAC 1105 College Algebra. We're in section 5.2 part B, where we're going to look at the graphs of logarithmic functions. And in this first example, I wanted to start by comparing logarithmic functions and the graph of one of those to the kind of functions that we graphed in the last section, which was the exponential function, because these kind of functions are inverses. In fact, we went through all these problems where we learned to rewrite logarithmic expressions as exponential functions. Well, in terms of graphing them, they are inverses. And when you graph inverses, you'll see that they form mirror images on either side of a line called y equal to x. And when I go to do the graph, I'll point that out to you. I'll put both graphs on one grid, and you'll see the mirror images forming on either side of the line called y equal to x. Also, what happens when you're dealing with inverses is that their x's and their y's change responsibilities. In other words, the domain of one function will be the range of the other one, and the range of this function will be the domain of the other one. So once you figure out what the domain and the range is for one of the functions, you can just rewrite them, switching them for the other function. So just some basic relationship between basic relationships between inverse functions. Okay, so I've started this first function. I'm going to graph it, then I'm going to state the domain, the range, the asymptote, and I'm also going to do that for the logarithmic function. So here's a table for f of x. It's just y is equal to 2 raised up to a power of x. That's this function right here. Y is the f of x, and then you have 2 to a power of x. For my x values, I'm going to plug in the ones that I plugged in quite often in the last section, just because they helped me to keep the values small for graphing purposes, and those were -2, -1, 0, 1, and 2. I plugged in -2 right here, so that gave me 2 to the -2, or in other words, 1/4, which is equal to 0.25. You can always put that in your calculator if you want to get that decimal version. Then I plugged in -1, so that was 2 to the -1, or 1/2, which is 0.5. Then I plugged in 0, which gave me a 1. I plugged in a 1 right there, which gave me a 2. And I plugged in a 2 right there, which gave me a 4. Plotting those points will help you to see the domain, the range, and the asymptote. So plotting this, -2, 0.25. Okay, -2, and then 0.25 would be about right there. -1.5 would be about right there. Over to -1 up to 0.5, a little bit higher than that one. 0, 1 would be right here. And then 1, 2 would be right here. And then 2, 4 would be right here. Whoops. Didn't go out far enough. So we'll look to 2, 1, 2, 3, 4, right there. Okay, so you can see these y values climbing, and then the axis or the line that this tail gets closer and closer to, that would serve as the asymptote. So this is what the graph of f of x looks like. Okay, so for purposes of the asymptote for this particular graph, that would be the x-axis, and this x-axis is also known as y equal to 0. So this particular graph has a horizontal asymptote. Okay, so horizontal asymptote, it is y equal to 0. And then as far as the domain and the range go, here's the domain. The domain, remember, that's a discussion about x's, so the x's go as far as -infinity, and then this, don't forget that it flares out to positive infinity. So -infinity to infinity for your x values. The range, on the other hand, is controlled by this asymptote right here. This asymptote represents y is equal to 0. Everything on the x-axis has a y value of 0, but yet this entire graph is above the x-axis. So all the y values on this graph are greater than 0. So everything from 0 to infinity would be part of the range. Okay, then as you go to the next graph, which is the g of x graph, that graph is y is equal to log of x base 2. And we learned in the last section, concentrating quite a bit on it, how to go from log form to exponential form, because you can't evaluate while it's like this. So when you're going into exponential form, you just simply push up this base, go to the other side, grab the item that's by itself. It will come over here to become the exponent, and the x will go over and take its place. So now we have this new equation, x is equal to 2 to a power of y, and you can make a table based on that. But being that these are inverse functions, again, the nature of two inverse functions is that their x's and y's shift responsibility. So you already have a nice table up here where you have built the x's and the y's, and you've already gone through the part of plugging it in and seeing what the resulting values are. So you could just take those values and switch the x's and the y's. And you would have the actual values that, if plugged in here, would actually, when you take 2 and raise them to those y values, would be your x values. But let's check that out. Let's verify that. If we just take those x's and y's and switch them, as we should be able to do if these are truly inverses, log of x base 2 and y equal to 2 of x, then these values should make sense even if I was to come back here and plug them in. So let's see. Okay, so we had negative 2.25. Let's switch it and get 0.25 and negative 2. Then we had negative 1.5, but we'll have instead 0.5 and negative 1, switching the x and the y for each pair. So 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. And 2, 4 becomes 4, 2. Now, even when I go and check, use these values as though I got them from actually plugging in, they should work. Now, when you're plugging into something like this, always plug in on the side where the operation is, not for the variable that's by itself. That is just a result of what happens over here. So when I plug in negative 2, I get 2 to the negative 2, or 1/4, which is 0.25. So that is valid. When I plug in a negative 1 here, that's 2 to the negative 1, or 1/2, which is 0.5. That's valid. When I plug in a 0 there, I should get a 1 for x. That's valid. So each of these pairs checks out. When I put this 1 in here for y, I get a 2. And look at the x partner. When I put in a 2 for y, 2 squared would be 4, and that's the x partner. So switching them does work, but yet I didn't have to really think about plugging them in, but wanted to do so so that you could see that they verify and check out. Now I'm going to plot these pairs so that I can tell again domain and range, but again I already know the domain and range, because if the domain for this was negative infinity, then that becomes the range. The domain and range switch responsibilities when you move into the inverse graph. So once again, what is my new domain? Well, it's what the range was. What is my new range for this logarithmic function? Well, that's what the domain used to be. And what is my new asymptote? Well, instead of having a horizontal asymptote at y equal to 0, I'm going to have a vertical asymptote right here. But you'll see that I'll have a vertical asymptote right at the y-axis, which is called, another name for the y-axis when you're naming it as an equation, as you always have to do when you're giving an asymptote. You have to give it as an equation. it will be this line that the points get very, very close to. Therefore, it serves as the asymptote, but it'll be a vertical asymptote. So right here, vertical asymptote will be x equal to 0 rather than y equal to 0. Okay, so let's see, let's plot these points. I'm going to x is equal to 0.25, but all the way down to -2. I'm going to 0.5, but then down to -1. I'm going to 1 and then 0, out to 1, 0 up in the air, then I'm going to 2 and then up 1, out to 2, up 1, then I'm going to 4 and then up 2. So 1, 2, 4, up 2. You see this climbing and then getting very close to the y-axis. So this is what we call mirror images on either side of the line called y equal to x. This is the line called y equal to x. Goes right through the origin. And if you were to crease your paper right here on this line, you would have images that superimpose on each other when you fold the paper over. Okay, so that completes that problem. Now let's go to the next problem. Here I just did a review of a table that has all the different transformations on it. You can call it a translation or a transformation. We've been talking about all of these things in the previous section just for exponential graphs. But this conversation of horizontal, vertical shifts, reflections, horizontal stretching and shrinking, vertical stretching and shrinking, that can be had for any shape. So this is just a review of that. That if you have numbers that are added out here, that is a vertical transformation. If it's positive c, it goes up c units. If it's negative c, it goes down c units, because that's an act upon the y values. We don't reverse operations there. However, if the positive c or negative c is included with the x expression, you have to reverse the operation. So instead of moving c units to the right, it would be c units to the left, because we'd really be using a negative c here. Here we'd really be using a positive c. You have to always reverse that operation for horizontal translations. Reflections, we've talked a lot about that in the last section. When the negative multiplier is out front, it flips it over a horizontal line. And when the negative multiplier is included in the x expression, it flips it over the y-axis or some vertical line. We also have vertical stretching or shrinking. So if the value is out front like that, that's vertical, either vertical stretching or vertical shrinking. It depends on the size of the c value. So if that c value multiplier is greater than 1, that's a vertical stretch. And if that c value is between 0 and 1, in other words, a fraction where the top is less than the bottom, that'll be a number between 0 and 1, and that will vertically shrink the graph. On the other hand, if the multiplier is involved and part of the x expression, then that has to do with horizontal stretching or shrinking. If that c value is with the x, a multiplier of the x expression, and it's greater than 1, that's horizontal shrinking. And if that c value is a fraction, where the top is less than the bottom, then that'll be a value between 0 and 1, and it will horizontally stretch the graph. So look to see where the multiplier is. If it's out front, that has to do with vertical stretching or shrinking. And if it's part of the x expression, that's horizontal stretching or shrinking. Okay, in this problem here, we're going to be graphing log of x base 2. No transformations, nothing added or subtracted, or no multipliers, whereas this one does have a transformation. So this will be perceived as the parent graph. And this will be the transformed graph. Okay, so here is a table for log of x base 2, but again, you cannot evaluate these while they're in log form, so always know how to rewrite them in exponential form. Push up that base. Go grab the item that's by itself. It'll become the exponent, and this x jumps over and takes its place. This is what you are making a table for. Okay, when you make this table of values, you are always plugging in on the side that has the operations happening, not for the variable that's by itself. And I know you're going to be tempted to plug in for x. Students often put the value in the wrong place, but we're putting the values in for y, so you've got to kind of force yourself to look at that. That's what we're plugging in for, so we can plug nice small numbers in like this. Unless the base is real big, then maybe you don't even want to use the -2. 1 and 2. Okay, so when we're doing this problem, we had already gotten these values on the previous page. We did 2 to the -2 and got a 0.25. We did 2 to the -1 and got a 0.5. We did 2 to the 0 and got a 1. We did 2 to the 1 and got a 2. We did 2 to the 2 and got a 4. So it's a table from the previous page, now acting as the parent graph. Okay, go and graph these. And then you can answer domain, range, asymptote, and so forth. So 0.25 is out about that far, just a tiny hair past the y-axis and down to -2. Then you have 0.5, a little further out, but only down to -1. Then you have 1, 0, out 1, 0 up in the air. Then we have 2, 1, so 2, 1. Then we have 4, 2, which is 2, 3, 4, and up at 2. Okay, so there's your graph right there, and from that graph you can nicely tell what the vertical asymptote is. This is the asymptote. The entire graph is to the right. These points just get close but don't actually blend with this. So it is a vertical asymptote, the y-axis, which is called x equal to 0. So vertical asymptote, the equation of the vertical asymptote is x equal to 0. The domain, all the x's that are on this graph, well, all the x's on this graph, the entire graph is to the right of this value x equal to 0. So all the x's are 0 or greater. The y values, this actually gets bigger and bigger and higher and higher and higher. So we say that these y values get higher and higher, so they go to positive infinity. And then they go as low as negative infinity. So the range is negative infinity to positive infinity. Okay, with respect to the next graph, which is just an alteration of this parent graph. Read the commands so that you don't have to plug in each time for the new value. So here for, this was f of x. This is all the f of x information. This is all the g of x information. And it's just y is equal to log of x minus 1 base 2. So you would put this in exponential form. You would raise up this base, go grab the item that's by itself. It would become the exponent, and then the x minus 1 would jump out and take its place. And if you were going to plug into this thing, if you were going to plug in various values for y, you'd actually have to have one side where you have one variable all by itself before you could truly start plugging in for it. So you'd have to bring this -1 over here, and it would become a positive 1 at that point. That way you could plug in whatever you want for y as the exponent. You could go 2 to whatever power, then add 1, and that would give you your x values. But that's a lot of work. So instead of going through all of that, we learn how to read the commands that are being given to us so that we can just take the values from the parent graph and transform them according to these commands. So notice that it is an operation on x that you're doing, and every time you do an operation on x, you reverse the operation. This is only when you're working with x's. So this would be x plus 1. Okay, so that's all we're going to do. Nothing is being asked of you as far as changing the y values. Only the x's are being changed. So with respect to your new table, we are going to take the x's and add 1 each time using the values on the parent table. But we're going to leave the y's just as they are. Okay, so the y values from the parent table were -2, -1, 0, 1, and 2. However, the x values will be adding 1, so 1.25, 1.5. 1 plus 1, that'll make that 2. 2 plus 1, remember this is the game plan, take the x's off the parent table and add 1. 2 plus 1 is 3, and 4 plus 1 is 5. And then we'll go and graph these points, and that would be the same as the values that we would have gotten if we would have started plugging into this. But look how much more work it would have been. We would have had to have taken the -2 right there, gotten a 0.25, then added the 1, which would give us this. Then when we plugged in -1, we would have went 2 to the -1, gotten 0.5. 0.5 plus 1, 1.5. Then we would have to put the 2 in there. 2 squared is 4. 4 plus 1. Let's see. What did I do here? Okay. Oh, no. The next one was 0. Sorry, I was talking about the wrong one. So the next one down was 0. So if you would have put a 0 right in there, that would have been 1. 1 plus 1 is 2. Then the next one down was 1. 2 to the 1 would have been 2 plus 1 would have been 3, and so forth. Then if you would have put the 2 in there, finally, that was the last value. I was doing that too soon. 2 squared is 4. 4 plus 1, 5. That's a lot of work. So these we got super easy by just taking the x's that were already here and adding 1. And these we just copied. So again, that's a skill that I keep reinforcing throughout each of these sections. Learn how to read the commands and then just perform them on the values from the simple table that comes from the parent graph. Okay, so going and plotting these now. Let me get this out of the way. Okay, we're going to go to 1.25 and then down to -2. So 1.25 and then down to -2. Okay, then we're going to go 1.5 and down to -1. 1.5 down to -1. Then we're going to go to 2 and 0. Then we're going to go to 3, 1. Then we're going to go to 5, 2. 4, 5, up 2. Whoops. Yeah. And so here we are climbing just like the other points climbed, but this time, this point right here that's at 1.25, just a hair past the 1, and that's because now 1 is acting as the vertical asymptote. And that's because everything, as we went from f of x to g of x, all that happened as we went from f of x to g of x is that we horizontally shifted 1 unit to the right. That's what it means to take each of your x values and add 1. It pushes everything over 1 unit to the right. So now that vertical asymptote is x equal to 1. That's your vertical asymptote for the g of x function. Okay, as far as the domain and the range, let me put everything here together. Okay, so your vertical asymptote now was just x equal to 1. The domain would just be, okay, so these are all your, this entire graph is to the right of that vertical asymptote. So it would be all x values greater than 1 for this new g of x graph. Okay, and then the range goes as high as positive infinity and as low as negative infinity. Nothing is different about that range. The range on these logarithmic graphs are always negative infinity to infinity. When we were studying the exponential graphs in the last section, it was the range. It was the domain that was always negative infinity to infinity. Now it's the range that's always negative infinity to infinity, because as I stated when I started this section, the domain and the range switch responsibilities. So again, it was the domain that used to always be negative infinity to infinity when we were in the last section studying exponential functions. Okay, that completes that problem. And then we come to this one. And in this problem, we have f of x is equal to just log of x. That'll serve as the parent graph. And then we'll do the alterations suggested by this graph. You may want to rewrite this just because it'll make things seem more familiar, where you have the multiplier out front, which flips the graph over some horizontal line. Sometimes it's the x-axis. And this 3 is the same thing as having a 3 back here. And then this is going to lift the graph 3 units. It's going to lift the points 3 units if you're comparing it to this parent graph. Okay, so let's get this in yx form. This is what it looks like in yx form. By the way, you know that you always have to rewrite these log equations in exponential form. So therefore, you need to know what base to lift up so you can put it in exponential form. When a log does not show a base, that means the base is said to be 10. So when we put this in exponential form, it's going to be 10. We'll grab this item that's by itself. It will become the exponent, and this x will jump over and take its place. So these two things switch sides, and this just gets pushed up as the base of the exponential expression. So it is from this equation that you're getting values for your table. Now, because that base is so big, you might not want to go all the way from -2 to 2. You can, but you're going to get very tiny values. And you can do -2 to 2 if you want. I'm just going to stick with -1, 0, and 1. Whoops, I'm putting them on the wrong side. Never plug in for this item that's by itself. Plug in for the variable that's involved in the operation, where you're going 10 raised to a power of y. Okay, so 10 to the -1, when you plug this in right here, 10 to the -1 is the same thing as 0.1. You can put that in your calculator if you like. Then when you plug in this, the 0, 10 to the 0, that's just 1. And when you plug in a 1, right there, you would have 10 to the 1, and that's 10. Okay, so if you plot those 3 points, you would have 0.1, just a tiny hair past the y-axis, if you're plotting this for x and this for y. So be like right there, barely separated from the y-axis. And then if you go to 1, 0, you're out 1 and 0 right there. And then if you go to 10, 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, and you're up at 1. And so going like this, and then this is going to serve as the asymptote. And so this will be your f of x function. Okay, and you can see from the graph here that the vertical asymptote is right here, x equal to 0. The domain, which is the x values, all these x values are greater than 0. They're all to the right of that asymptote. The range, I know this looks like it levels out, but it actually gets higher and higher and higher going that way. So we say that the y values go to positive infinity, and then the y values on this tail go down to negative infinity. So the range is always negative infinity to positive infinity on these logarithmic graphs. Okay? Those are all the things asked for: asymptote, domain, and range. Okay, then for the g of x function, which is this one right here, when you put this, even though we're not going to evaluate this, if you were to put this in exponential form, this would be y is equal to negative log of x base 10. When you don't see the base, it's said to be 10 plus 3. But to even get this in the shape where you were ready to plug into this thing, you would have to get this logarithmic expression by itself. This would have to be by itself before you get it into exponential form like I did to create this table. That would mean bringing the 3 over here, at which point it becomes negative 3. It would also mean getting rid of this negative multiplier before you start raising up that base and putting it in exponential form. You'd have to divide this side by negative 1 and this side by negative 1, which would turn this into negative 3 divided by negative 1 would be positive 3. Y divided by negative 1 would be negative y. Then you would finally have yourself in a situation where you're ready to put it in exponential form. You would have, here's your log form. It's got a base. And if you want to put it in exponential form, you would raise up that base, go grab the expression over on the left-hand side. That would become the exponent, and this x would come over and take the place of this entire expression. So that you would finally have one variable by itself, and then the other side would be where the entire operation is going in. You'd be choosing values for y, but that is too much. So you learn how to do it an easier way, which is to act out the commands that are different from the parent graph. So look at what this is saying to you. Okay, notice that neither one of these things has to do with the x, because if this had anything to do with the x, it would be in parentheses, and you would know to reverse the operation. But since it's not, that means you're acting on the y. So one of the things you're going to do is add 3. Remember, when we do things to the y, we don't reverse the operation. So we're going to be adding 3 to the y. This is also not involved in this x expression, so this is an operation on y. So we'll be adding 3 to our y's and multiplying our y's by negative 1. And there, you have to, observe order of operations. When multiplication and adding are involved, you multiply first. So instead of plugging into this crazy thing right here, all we're going to do is make a table here. The commands that are being suggested by this transformed log function is that on our y's, we're going to be multiplying those y's by negative 1 and also adding 3 in that order. Multiplying first, then adding 3. We're doing nothing on the x's, so the x's will stay as is. We're not going to change those. And we're getting these x's from the parent table. So the x's were 0.1, 1, and 10. 0.1, a 1, and also a 10. And then the y's, we have to do these things to them. So when you take this negative 1 and multiply it by negative 1, which is this plan right here, it will be positive 1 plus 3 is 4. When we take this y value and multiply it by negative 1, as is the plan, we still get a 0, but then we add 3. And when we take this y value and multiply it by negative 1, it's negative 1 plus 3. Negative 1 plus 3 is 2. And now we can plot this to get our g of x graph. So let's see, we're going to go to 0.1 and then up to 4. 1, 2, 3, 4, and that'll be right there. Then we're going to go to 1 and up to 3. 1, 2, 3. Then we're going to go to 10, 2, 3, 4, 5, 6, 7, 8, 9, 10, and up to 2. Then we have this graph. This is acting as the asymptote. And then we're going to talk about the asymptote, the domain, and the range. So the only way that this asymptote would have changed is if we would have shifted the graph over for this transform graph. And that wasn't what's happening here. All that's happening were operations on the y value, the addition of 3 and the multiplication by negative 1. So it's going to have the same asymptote. Vertical asymptote is x equal to 0. As far as the domain goes, you can just look at the actual function and tell what the domain is, but of course you can also look at the graph. When you look at this graph and consider the fact that this is the vertical asymptote, look at how the entire graph is to the right of that vertical asymptote. So all of the x values on the domain for the g of x function are 0 to infinity, of course not including the 0. As far as the range values go, the range values are always negative infinity to positive infinity. Okay, and the transformations that happened as you went from f of x to g of x is that it was shifted up 3 units. With respect to the parent graph, and horizontally reflected because of that negative value. And I wrote those all right here, just by looking at the equation above. Vertically shifted up 3 units, that was the plus 3 at the end of the function. And I can write that function right here so you can actually look at it as you copy these notes. And then horizontally reflected because of that negative multiplier. Those are just comments about what's happened as you go from the parent graph to the transformed graph. Okay, going to this next problem where you're comparing natural log of x and natural log of x plus 5 minus 2, and we're going to put them on the same rectangular coordinate system. We're going to state the domain, the range, and the asymptote of each graph and the transformation required to go from one graph to the next. Okay, so working on ln of x, so this is the f of x function. So it's y is equal to ln of x. All ln of x functions have a power of e, or not a power of e, a base of e, excuse me. And if you put it in power form, then it's e to the y is equal to x. And you can get a table just like that. but do remember to plug in your values for y. And you can plug in -2, -1, we did this in the previous section, and also 2. And I'll just round these off. So when you plug in e to the -2, it's 0.135 or 0.14 approximately. And when you plug in e to the -1, that would be about, I'm going to round that off to 0.4. And when you plug in 0, e to the 0 is just 1. And when you plug in 1, e is 2.7, almost 3. And when you plug in 2, get about 7.4, just to get a little idea of where you're at, and then you can plot these points. And then when we go to get the values for the parent graph, we can just work off of these values right here. Okay, so plotting these points, we're going to go to 0.14 down to -2. Almost right on top of that y-axis. Then when we go to 0.4 and down to -1, that'll be a little further out, and then down to -1. Okay, then we're going to go to 1, 0. That's out 1, 0 units up. Then we're going to go almost to 3, 2.7, and then up to 1. Then we're going to go almost to 7.5. So this would be 3, 4, 5, 6, 7, 8, and 7.4 would be about right there, and we're going to a height of 2. Okay, so just approximating like that. This is your f of x graph, and you can answer all those questions. Vertical asymptote is this y-axis, x equal to 0. Domain is all x values greater than 0. The whole graph is on the right side of x equal to 0. So 0 to infinity. The range is always -infinity to infinity for the logarithmic graphs, and that's because this spans up, 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 up to positive infinity, and this goes down to -infinity with respect to your y values. Okay, then when you're going to do the other table, instead of, going through all the moves where you put it in exponential form and all of that, you can just read the commands here, alter the table, tell the domain, range, and asymptote right from the graph. So for g of x equal to ln of x plus 5 minus 2. Okay, look at the things that you're being asked to perform. This says add 5 to the x, but when you're doing any operation on x, you're going to reverse that operation. So when we go to do our table, we don't have to keep plugging into this or put it in exponential form. We can just take those x values. Don't forget to reverse this operation. We're really going to be subtracting 5 on our x's. This has nothing to do with the x expression, and therefore this is an operation on the y values. And we don't reverse the operations. This, we reverse the operation. Anything on x's. But on my y's, you actually do as it states. So using these values right here, we have things to do to the x, things to do to the y. I'm going to do the y's first. So each y value you're going to subtract 2. So -2 minus 2, -4. -1 take away 2, -3. 0 take away 2, -2. 1 take away 2, negative 1. And then one more. 2 take away 1 is 1. Okay, then on my x's, we're subtracting 5. You might want to get your calculator involved. So it's going to be 0.14 minus 5. So negative 4.86. Then it's 0.4 minus 5. And that's negative 4.6. Then the next x value was 1, and we're subtracting 5, just like the little plan says right here. So 1 minus 5 is negative 4. Then we're going to take 2.7 and subtract 5, and that's negative 2.3. And then the next x value down was the 7.4. And we're going to be subtracting 5, so that would be 2.4. Okay. Now we have these two tables. We did this operation on our x's, this operation on all our y's, grabbing these values that we were doing this and this to from the parent table, rather than plugging into this over and over again after writing it in exponential form. So we skipped all of that and just took the easy route to transforming this graph. Okay, so now let's plot these so that we can tell what the vertical asymptote is, the domain and the range and all of that. And as we look at this function, we know that we were going to shift horizontally 5 units to the left, and this is as we go from f of x, the parent graph, to g of x. We can tell what the things are that are happening. We are horizontally shifting 5 units to the left, and that's because we used x minus 5. That's because we reversed the operation. Okay, so those are some things that happen. We also shifted the graph is also going to shift vertically down 2 units, and that's because all the y values got 2 subtracted from them. So we're explaining what the transformation is, and now let's make it visual by actually plotting these points. So we're going to negative 4.86, 1, 2, 3, 4, 5, negative 5, negative 4.86 would almost be right at negative 5, and that has a y partner of negative 4. So 1, 2, 3, 4, that's going to be about right there. Then the next one is negative 4.6, slightly to the right of that, but not much. Negative 4.6 is going to be right about there and down to negative 3. Okay, then we're going to be at negative 4. So over to negative 4, 1, 2, 3, 4, and then down to negative 2. And then negative 2.3. Negative 2.3 would be negative 1, negative 2, negative 2.3 would be about right down there. And then negative 1. So negative 1, negative 2, negative 2.3, and negative 1. Okay, then it's 2.4 and 1. So then 2.4 would be 2, 2.4, and then moving up to 1. About right there. Okay, so This graph was getting very, very close to this line right here. These points got closer and closer to this line right here. And that's because the entire graph moved with respect to the parent graph, it moved 5 units to the left, which brought the vertical asymptote that guides it 5 units to the left. So these points came up right against it and then began to get higher and higher. Okay, so this was my parent graph. And then you can see that that entire g of x graph moved 5 units this way. This is the asymptote that controls it. Whereas the y-axis was the asymptote that controlled the parent graph. Okay, so this is called x equal to -5. Okay, so the vertical asymptote was at x equal to -5. The domain, all x values are greater or to the right of 5, so 5 or greater. And then the y values, the range for all of these logarithmic graphs, -infinity to infinity. And I had already explained here what was the transformation as you went from the parent graph to the transformed graph. Okay. Okay, so one more problem here. We are going to use the parent graph log of x and the transformation techniques to graph h of x. So when you're going into My Open Math, you're going to have to graph a point on the asymptote, and then you're going to have to graph 2 points on the actual log graph. So we've had plenty of examples thus far about how to use the parent graph to get the transformed graph. And so we're going to just do that all over again, only we're going to respond to the type of questions that are in My Open Math where you're picking these transformations. So you can tell these things right off the bat before you even graph it. This is a vertical shift 4 units down. It is something that you would do on the y. You would take the y values and subtract 4. This is something that you do to the x. This looks like, this appears to be x multiplied by -1, but remember, we reverse those operations on x. So we're going to take our x's and divide by -1. Now I know you get the same answer either way, but it's good to memorize that you're reversing operations always when working on x, because what if this would have been x times -2? Then you better be dividing by -2 instead, or else you get completely different answers. It's just because this is a -1 that you get a same answer whether you reverse it or not. But it does make a difference as to what it reflects over. When the negative is here versus out front, those are different kind of reflections. So when we pick here, what's happening, it's going to vertically go down 4 units. Okay, so let's see. We're going to shift the graph 4 units down. That's one of the things that's going to be happening. And we're going to, let's see. Where are the reflections? Reflect the graph about the x-axis. Flipping over the x-axis is when the negative is out front. Let's see, where else is there? Reflected about the y-axis. When we reflect vertically over the y-axis, that's because the negative is there. So that would be this one. Okay, now actually carrying everything out. This is going to be for f of x, just like what I did in all the other examples. F of x is y is equal to log of x, no base there, therefore it's a 10. You want to rewrite that in exponential form, it would be push up that base, go grab the item that's by itself, it becomes the exponent, and we have the x jumping over to take its place. So again, once again, switching sides and making our table from this, which we have already done in a previous problem in this section. Okay, base is pretty big, so I'm going to stick to -1, 0, and 1. -1, and I'm supposed to be putting that there. 0 and 1. So when you go 10 to the -1, you get 0.1. You could always put that in your calculator. You get 1/10. And when you put a 0 in there, you get a 1. And when you put a 1 in there, you get a 10. Okay, so plotting this, okay, we would be 0.1, -1. And we would be 1, 0. We would be 10, 1. And you saw this graph in a previous example. Oops, missed the point. Okay, so there's your graph. This is acting as the asymptote because the points are getting closer and closer to that line. So this is behaving as the asymptote. That's called x equal to 0, that vertical asymptote. That also controls the domain. So right from that vertical asymptote, we know that the domain is all x values greater than 0. I guess there's a space for them right here. Okay, and then the range for all of these logarithmic functions is -infinity to infinity, the equation of the asymptote, x equal to 0. So I just wrote it twice. Okay, now we're going to go after the g of x function, doing the operations that we just discussed above. So with this, that's actually called h of x. So the h of x function is log of -x minus 4. Okay, so now what we're going to do is make our table for h of x. I'll make you some food, baby. Mama's going to make you some food. Okay, so then, sorry, I'm busting into my videos talking to my animals. All right, so then let's see. So we were dividing each one by -1 on the x's. So that's -0.1. And then we're going to take 1 divided by 1, and that's -1. And then we're going to take 10 and divide by -1, and that's -10. And then on our y values, this is an operation on the y values, and we're going to be subtracting 4. So here were the x's divided by -1, and with the y's, we're subtracting 4. That's an operation on y. This is an operation on x. So my y values were -1, but if I subtract 4, it's -5. My y value was 0, and when I subtract 4, it's -4. And when I take the 1, that was a y value in this parent table, and subtract 4, it becomes -3. So I have these values now for my new graph, for my h of x graph, but without doing any kind of crazy plug-in. So let's see, when I go to graph these now, let me go to -0.1, which is over here, but down to -5. And that'll be about right there. And then when I go to -1, all the way to -1, then I'm going down to -4. And then when I go to -10, come down to -3, -1, 2, 3. Okay, so basically what's happening here is, let's see how I can connect these. Shoots off this way, comes through here. And goes down like that. So we still have a vertical asymptote of x equal to 0, but what happens is it's flipped over that y-axis. It has reflected over the y-axis, as you can see right there. It's been yanked 4 units down, and this is what caused the reflection over the y-axis. So it's a comparison of the two graphs. Okay, and that completes that problem. But with respect to domain, range, equation of asymptote, I'll write them here as well. So the domain of the g function well, let's talk about this domain. Here is this asymptote right at x equal to 0, and for this g function, this is, or not, I keep calling it the g function, I'm sorry. This is called the f function. This was the original function over here that had a domain of all x values greater than 0. And then this other function that I graphed is on the left side of that same asymptote. So this has all x values that are less than 0 rather than greater than 0. So this domain goes, my x values are -infinity to 0, but not including 0. And then that range is always the same. Straighten up with what I'm writing here. And then the range of the h function is, as all the ranges are, -infinity to infinity for those logarithmic functions. Okay, then going to some straight problems where all you're doing is talking about the domain. So please try to remember that for log expressions, look at the one thing that is a no-no. When you're doing a log, you may not put any kind of negative in there. See how it quits? Because that is not part of the domain. Also, when you try to do a log expression, you cannot even put a 0 in there. It'll quit on that also. So that suggests the definition that came up a couple sections ago, or the previous section, that that domain has to be greater than 0. So the domain is figured out based upon this argument. So if you want to know what the domain is, without any kind of graphing or anything, it is taking the argument of the logarithmic expression and making sure that you keep it greater than 0. Okay, so when you solve this, this would be like this, and you would end up with 2x greater than 4. Divide by 2, divide by 2. And you would end up with x is greater than 2. Okay, so all values greater than 2 is what the domain would be. So think about the relationship between the domain and the asymptote. If all the x values are to the right of 2, that's what 2 to infinity means, everything to the right of 2, that means that there must have been an asymptote at x equal to 2. Likewise, for this g of x function, for any logarithmic function, you need to keep that argument greater than 0. So when you're solving this, it would be bring this -10 to the other side. It would then be +10. You would then have -5x is greater than 10. But remember that when you're solving an inequality and you divide by a negative, that switches the direction. So this would actually be x instead of greater than, it would be less than, and this would be a -2. So if you're saying that all the x values are less than -2, that's all x values on the left side. Those x values go to -infinity. So that domain would be -infinity to -2. Okay, and therefore the asymptote would be at x equal to -2, and the entire graph would be on the left side of that asymptote. Here you're going to have two stipulations for asymptotes. So again, you're always attempting to keep this argument greater than 0 so that the logarithmic expression will be defined. But when you're solving second degree inequalities, that calls for cut points on a number line and then testing the intervals created by the cut points. First thing you do is factor this. And this factor is easy enough. This has a common factor of x that you could take out. So you can factor this expression as x, pull out the x, and then x minus 2. Factoring it will allow you to determine what the cut points are on the number line. What would make this 0? You could plug in a 0 here and it would turn this whole side 0. So one of the zeros is x equal to 0. So put that on your number line. I really shouldn't put that one there. I'll put one number here and one number here. Oh, no, this will work. And then what would make this 0 would be x equal to 2. So these serve as the cut points. If you remember from previous review chapters how to solve a second degree inequality, those call for cut points, which are really the zeros belonging to these factors. Then you have to test a number in each interval. So when you would test -1 in this original inequality, test -1, you can test +1, and you can test 3. And you're testing it right in here, x squared minus 2x, wanting to know if that is greater than 0. So if you put a -1 in there, you get 1 plus 2. That most definitely is greater than 0. So when testing -1, which is in this region, you get a yes. When you go to test the next number, I'm going to recycle this. So this will be a 1, this will be a 1. Let's see what you get. Okay, so this would be 1 take away 2. You would end up with -1. Is that greater than 0? No. I think it's just easier to rewrite it. So then test it one more time, seeing if it's greater than 0 or not. Number over here that we're testing is 3. These are our test points. So this would be 9 minus 6. Is that greater than 0? Most definitely. 3 is greater than 0. So we have everything to the left of 0 working. So the domain is everything from -infinity up to, but not including 0, or anything from 2, anything to the right of 2, anything to the left of 0. So it's like you're going to have an asymptote right here on your graph, right at 0. And all these x values to the left of it, they'll be a part of the graph here. And then at 2, or to the right of it, there'll be another asymptote at 2, and then all the x values to the right of that will be good. So there's an asymptote at x equal to 0 and x equal to 2. And that completes 5.2b. I believe that's the last problem. Yep, it is.